Hello everyone, welcome back to a Chemistry with Suki video. Today we're going to be going through the hybridization of IF3, and through this hybridization we're going to be learning a lot of different things such as the types of bonding, key terminology. We're going to learn the correct procedures and steps of drawing the Lewis dot diagram of IF3, as well as going through the electron configuration, energy level diagram, and hybridization of IF3. And don't worry, if you don't know what these are, you will learn them today. And we're also going to go through some grade 11 review by doing some intermolecular forces as well as intramolecular forces and what these mean for IF3 in itself through its properties. So let's get started. Now we'll be looking at the types of bonding that may occur in a given molecule. The first one we'll be talking about is the covalent bond. Covalent bond is, let's say you picture yourself going with a friend. Yeah, it might be hard thinking about you having a friend, but it's possible in the fake world. Am I right? Just kidding. So you go out with your friend and you buy a pizza and you pay half and half and you equally share that pizza. That is essentially what a covalent bond is when there is an equal amount of sharing for electrons. Polar covalent bonds is something that's different. It is when, let's say, your friend buys an extra large pizza but you don't want all of it or don't even want much of it, and they pay extra on the share of that pizza so they get more slices. That is basically what's happening with polar covalent bonds. Polar covalent bonds is when there's an unequal sharing of electrons, or in our case, more pizza slices for your friend. And how is this represented is mathematically through the electronegativity chart right here. And we use a Greek symbol called delta, which means change in. Let's say where there is hydrogen bonded with oxygen. Hydrogen is right here, and oxygen is right here. So what you do is you take the electronegativity number right here, 3.5, and you subtract it with 2.1 right here. So let's do that. We write the Greek symbol delta, delta En, and that is going to be equal to 3.5 minus 2.1, which is 1.4. And 1.4, let's create a number line right here. This would be 0.4 and this is 1.7. 1.4 will be right here. And what are these values that I'm going to circle right here? What are these? So before we get to 0.4, the range between here is a covalent range. That means that our electronegativity, when our delta En is actually from 0 to 0.4, then we have a covalent bond. And from 0.4 to 1.7, we have a polar covalent bond. And we can use this math to figure out what type of bonding is occurring in a molecule. So in this case, when oxygen is bonded with hydrogen, let's say in an example as water, then we have polar covalent bonds. Just like the pizza example we had from before, we have a new example. This time you have no money because you didn't get paid and you saved $0. So you're making your friend pay for that pizza that you guys bought from before and didn't split the cost. That's basically what happens when we have a coordinate covalent bond. So let's say we have our blue atom right here, X, and it has these electrons right here, and then it is sharing these two red electrons right here. However, you, the Y, isn't sharing any electrons at all. It's just like how you, your friend, as just paid for your whole pizza and you haven't done anything at all to contribute to that pizza. It's when one atom shares the pair of electrons where the second atom doesn't share them at all. That is what a coordinate covalent bond is. An ionic bond is the strongest type of bond we have to date, and that is because it has a one positive atom and one negative atom, which means there's a nonmetal bonding with a metal. And a good example of an ionic compound or ionic bond would be NaCl. And how do we confirm that this is a ionic bond? We see that the electronegativity. Remember that electronegativity number line that I had from before? We see that from 0 to 0.4. Let's draw this again. We see that from 0 to 0.4 right here, we have covalent, and then from 0 to 0.4 to 1.7 we have polar covalent, and then 1.7 onwards, we have ionic. And we could confirm that for NaCl by doing a simple electronegativity calculation. The delta En of this, we circle the chlorine, which is 3.0 electronegativity, and then Na, sodium, has a 0.9, so the delta En is 2.1, which lies on the ionic region of the electronegativity number line. And that means we have an ionic bond. Terminology that we really need to know today, and we'll be mentioning a couple of times, is lone pairs and resonance structures. So first we'll take out a blue pen and we'll draw the Lewis dot diagram for water, and that is just like this. So what are lone pairs? So when we look at a Lewis dot diagram, these are the two lone pairs that we have over here. And lone pairs are also known as non-bonding electrons. And these are because, well, they don't participate in bonds at all. And that is shown because we have a bond here and a bond here, but these electrons have nothing to do with it. Nothing at all. They do not do anything in terms of this bond. Which means that, well, these electrons are lonely. They are not participating with the other friends, which are the bonding electrons. Well, they're lonely in the corner, probably reading a couple of chemistry and biology textbooks, but we don't really judge in this classroom right here. But they're kind of lonely because everyone else is sitting there playing some games or something else while they're just reading some books. But we don't judge, and these are just known as lone pairs. Now, we'll be talking about resonance structures. Resonance structures are actually used when there's not only one way to represent a, well, molecule. And I'll be showing that in this example right here. So let's call our central atom X, and it is doubly bonded to, let's say, A, and singly bonded with A, and then singly bonded with A. Now, this can be drawn in a couple of different ways, and this is because electrons tend to wander, which means that there's only one way to draw a resonance structure or Lewis dot diagram for a singular molecule. So we can see here that, well, it could be doubly bonded to A here, and then singly bonded to A here, and singly bonded to A here, but then it could also be drawn as X singly bonded to A here, singly bonded to A here, and then doubly bonded to A here. So these are our resonance structures, and it is basically a multiple of different ways to draw one Lewis dot diagram in order for it to be completely accurate. However, our IF3 molecule today, well, it doesn't have resonance structures at all, so we won't have to worry about it. However, we may see some lone pairs when drawing our Lewis dot diagram. So keep that at the back of your head because you might have to use this terminology in a later slide. One of the key pieces of terminology that we need to know is the difference between octet and non-octet molecules. Non-octet molecules, when these conditions are met, then they are a non-octet molecule. Otherwise, it is a octet molecule, and it is simple as that. So every time we try to draw a Lewis dot diagram, the first thing that we need to look at is if it is a octet molecule or a non-octet molecule. So let's say we're drawing the Lewis dot diagram of sulfur hexafluoride. Then we see that since our surrounding atoms is greater than 4, it is 6, and 6 is greater than 4, then this condition is met. And also, since fluorine is a halogen and sulfur is the central atom, that this condition is met. But the thing is, when we're trying to go for speed and we're trying to go for a good mark on a test and we're trying to finish, then we know that, well, this is the only condition that needs to be met, so we know that this is a non-octet molecule. So let's go back and see another example. Let's take out a different color pen. Let's say we have boron trifluoride. Now, we see that this condition is met. Oh, since that is met, then it is a non-octet molecule. Now let's say we have SO4. Then we know that, well, sulfate is an octet molecule because none of these are actually met. And as simple as that. We just need to know if these are actually met, and if none of these are met, if none of them are met, then it is an octet molecule. Now we'll be talking about hybridization and the four-step process that we have right here in order for us to be successful when solving these hybridization questions. So what is hybridization? Hybridization tells us that the central atom, in our case iodine, makes new orbitals before bonding with the surrounding atoms, in our case fluorine. These new orbitals created by iodine are called the hybrid orbitals, and they're formed by combining the orbital types s, p, and d, and these must all come from the same energy level. So the four-step process we have today is first to draw an accurate Lewis dot diagram, second is to have a accurate condensed electron configuration, and using that we'll be creating a condensed energy level diagram, and then finally we will be doing the actual hybridization and showing how our iodine is creating hybrid orbitals. Now we will be drawing the Lewis dot diagram of iodine trifluoride, or IF3. As a reminder, a Lewis dot diagram shows how the electrons are situated around the atoms of a molecule. The first thing that we need to look at is the chemical formula. So let's write that down. IF3, and then we'll change our color to orange, and we'll do a little bit of investigation. So we look at our chemical formula here, and we see that the central atom is iodine, right? So we look at our periodic table, and we say, oh, this is part of our halogens. And then we refer back to our non-octet or octet molecule rules, and we see that this passes one of the conditions for it to be a non-octet molecule. And as mentioned before, we know that non-octet molecules only have single bonds. So let's draw that out real quick. Iodine, and we see that has single bonds to fluorine. And then we say a question to ourselves: is this non-octet or is this octet? And we realize that this is non-octet, so we only use the method that is not have-need. This is what I call the have method. The have-need method is a special method that we use to draw the Lewis dot diagrams. However, since this is a non-octet molecule, we cannot use it. And if you do, you will get a wrong Lewis dot diagram, and that is not good because you'll lose a lot of marks on your test. So we write down the have number, which is the amount of valence electrons that we have in our molecule, which is 7 times 4. How do we figure this out? Is that we know that fluorine and iodine are both part of the halogens, which means it has 7 valence electrons, and we know that we have 3 surrounding atoms and 4 atoms in total. So we have 28 electrons, and then we subtract 6 because we have 3 single bonds, and 3 times 2 is 6. So we go through, and that is 22 electrons. Now we're going to change our color to red pen, and we're going to draw in all our electrons. So draw it again. Be careful to always have 6, because none of us you'll lose some marks. And then we subtract 18 from the 22 that we had before. So now we have 4 electrons left. So when we have 4 electrons left, and we've subtracted the electrons from these surrounding atoms, we see that these electrons will actually belong to our central atom. And that is it. This is how our Lewis dot diagram of IF3 actually looks like. Now that we've done the Lewis dot diagram, we'll be doing the electron configuration, more specifically the shorthand electron configuration of our central atom, which is iodine. So we write down iodine, and then we put a colon beside it, and then we start the shorthand electron configuration. So our iodine is right here. So the noble gas that's before it is krypton. So we write down the krypton's element symbol in a square brackets. And then what's interesting about our periodic table is that as you go down, our energy levels actually increase. So we write down the energy level number, and then the first 2 columns are the S type orbitals, so we write 5s, and we've passed through 2 elements in the s-type orbital, so we cross those off, and we write the superscript of 2, and then we write 4d, and our d-type orbitals are from the column 3 to 12, and one thing to always remember is that our d-type is the special overlap, which means that our d orbital will always be 1 energy level that is prior to the energy level that we're in. So energy level you think you're in, subtract 1, and you'll get the d orbital's energy level number. So 4 in this case, and we passed through 10 elements, so we denote that by writing a 10 superscript, and then we passed 1, 2, 3, 4, and 5 to our iodine, so 5p5. And that is it. Now we will be drawing the condensed energy level diagram for iodine. So first what we do is we label our axes, potential energy, and types of orbitals. And then we switch to a different pen color, and we divide this chart up. And this is for our different orbital types, S, P, and D. And we write that down, right, as so. And then we write down our noble gas, and then the orbitals. So they will be all on top of each other, and that is how it's meant to look like. P will have 3, D will have 5, and S will have 1 orbital. And that is the correct way of doing it. And then now what we'll be doing is that since we are in the 5th energy level, we will write down 5. And since this is the S orbital type, we'll write down S, and then 5p, and then 4d. And this is all matching with our condensed electron configuration. Now what we'll be doing is we'll be switching to a red pen, and we'll be drawing in our electrons. Since we have 2 electrons associated with our S orbital, we'll be drawing 1 and 2, and these up and down half arrows denote that these will be spinning in different directions. And then we'll be moving on to our 4D, so 1, 2, 3, 4, 5, and then since all of my orbitals are filled with at least 1 electron, then we are pairing them. So 1, 2, 3, 4, 5. 5 plus 5 is 10, and that is what we have on our electron configuration. Now we go on again, and now we go to our 5p, and that's 1, 2, 3, and then we pair 1, 2, and that's it. That is how our condensed energy level diagram looks like. Now we take out a different color of pen, and we draw a big arrow. We write down hybridization, and that's what we'll be doing next. This is our last step of our master plan in order for us to solve these questions, these hybridization questions. This is arguably one of the most important parts of this question, as this is the actual hybridization. We're finally creating these hybrid orbitals. So what we do is we look at our Lewis dot diagram, which we accurately drew. Without this, we won't have our correct hybridized orbital. So make sure you have that. So we see that we have 2 lone pairs right here, and then when we looked at our bond definitions, we see that this is only a single bond here, and a single bond here. That means that we have 3 sigma bonds, so we'll write that down, 3 sigma bonds and 2 lone pairs. And it is definitely possible to have coordinate covalent bonds. However, our IF3 molecule does not have any coordinate covalent bonds, and the last type of bond that we might have is a pi bond, and that is when we have a double bond where one of our bonds will be a single bond and one of our bonds will be a pi bond. However, pi bonds do not participate in our hybridization, but they're still important to include in this list, but that is for a different molecule. Today's molecule IF3, we don't have to worry about that right now. Now the thing is, our d orbital type does not participate in our hybridization. So what we do is we take out a green pen or any different color pen as such, and we circle the parts that are going through our hybridization. Now what we do is that since we have 5 things listed right here, we'll have 5 orbitals, 1, 2, 3, 4, 5. And now that we have that, we take out a red pen yet again, and we draw in our electrons. Sigma bonds will have 1 electron, so we draw 1 electron like this, 1 electron like this, and 1 electron like this, because we have 3 sigma bonds. And then we have 2 lone pairs, 1, 2, and lone pairs are always, of course, in pairs, so we have 2 electrons in each orbital, 1, 2 again. And now, just to check your work on a test so you don't lose some marks, we see that we have 1 electron, 2 electron, 3 electron, 4, 5, 6, 7, and when we count here, we have 1, 2, 3, 4, 5, 6, 7. That means that we have done this correctly. Now we can move on to naming our hybridized orbital. So how do we name it? First, we create a little checkmark list. So this is for S, and S has one orbital, P has 1, 2, 3, and D has 1, 2, 3, 4, 5. Take out a different color pen, and we do checkmarks for every single type of thing that we have on our list. Since we have 5, we will have 5 checkmarks. So 1, 2, 3, 4, 5. And that means that we have, let's write down our energy level, which is 5, and then S, P, 3, and D. And that is our hybridized orbital for IF3. So let's get started on drawing this VSEPR diagram. The first thing that we need to do is determine how many electron pairs we have in this molecule. So the first thing we do is we circle them. So we do 1 here, 2, 3, 4, and 5. That means that our geometry of this molecule is trigonal bipyramidal. And well, the thing is, you need to have this memorized, not else you will fail your test because, well, you don't know anything about it. But you guys are good students, so you will be memorizing all of this. So we memorize this, and we know that this is a trigonal bipyramidal. So we write a nice therefore statement using a different colored pen. So we write down, therefore, the geometry is trigonal bipyramidal. And now that we have the geometry down, the thing that we need to do is actually determine the 3D diagram of this. And the one thing that you need to have memorized as well is that molecules with 5 electron pairs, 3 of them will be positioned in the same plane, where the other 2 electron pairs will not be situated in the same plane. And why is that? Is because in the VSEPR theory, it tells us that our molecules are not molecules, but rather the surrounding atoms are placed with respect to our lone pairs, and they're placed in such a way where it minimizes the repulsion and gives everything maximum amount of space possible in order for it to be able to experience the least amount of repulsion. So we take another piece of color, and then we draw the central atom how it was, same as before in our Lewis dot diagram, and then we have fluorine here, and fluorine here. And these are all in the same plane. Now, there's 2 things that you need to know. You need to know that this notation right here means into the page, and this notation means out of the page. Let's erase that real quick. And now that we know that our lone pairs will be either into the page or out of the page. And since we have 2 of them, well, it will be both. So we draw our into the page lone pair, and then out of the page lone pair. And that is our VSEPR diagram. Now the thing is, another important piece of information that we need to know is the bond angles. You should have this memorized by now, that a molecule with 5 bonding pairs, or with only 5 electron groups, either or will have a geometry of trigonal bipyramidal. However, due to our lone pairs, we may have a different shape, and that you have to memorize. In this case right here, we know that our shape is actually T-shape because, well, you could kind of see from our 3D diagram that it is a T-shape if you look at this side right here, because we know that our electrons are actually invisible and we won't be able to see them. They're just orbiting around. And this will be the T-shaped diagram right here. And the other thing that we need to know is we always have to draw our angles from bond to bond. And in this case, we actually have 2 different angles for this geometry. However, for IF3, we only have 1. So just as a reminder, you need to know that trigonal bipyramidal has an angle of 90 as well as 120 degrees if there's no lone pairs. But since there now are 2 lone pairs, well, we can cross this off right here because we don't have any angles in the equatorial axis. We only have axial angles, which is, well, what is present right now. And then now we need to take out a red pen and we need to draw this angle right here. And we could draw another angle here as well. It doesn't matter what you do, but you need to have at least one of these down. And we also need to know that every time we have a lone pair, we subtract 2.5 degrees. So since we have two lone pairs in this case, we will be subtracting 2.5 times 2, which is 5 degrees from 90. So now we write our final therefore statement. So let's take out our orange, and we write therefore our shape is equal to T-shaped, and we will have that memorized, and the angle, and sometimes it is angles, but in this case we have angle, and that would be with a red pen of 85 degrees. Do not use radians, Miss Mo will get mad. Now we're trying to find the difference between intermolecular forces as well as intramolecular forces and explaining what these are. So intramolecular forces are forces that are within one molecule. They're basically the glue that sticks that molecule together, just like how you would repair your grandma's old jewelry using Gorilla Glue because it's so important to you and you need to keep it stuck together in order for you to reminisce her. Just like that is how molecules are keeping together using intramolecular forces, and these are defined in a previous part of our video. They are ionic bonds. We also have the polar covalent and non-polar covalent bonds. And these are the three different types of intramolecular forces that we have, and they are within one molecule. And now we'll be investigating what intramolecular forces are in our IF3. So we write down the chemical formula, and we see that the two different atoms that we have, the two different elements we have is iodine and fluorine. So now we find the delta En, the change in electronegativity, and we know that fluorine has the highest electronegativity number, which is 4.0, and we know that iodine, looking back at our chart, is 2.5 in its electronegativity number, which means our delta En is 1.5. Referring back to the number line that we looked at beforehand, we see that this falls in the polar covalent range. That means that we have polar covalent bonds in our molecule. Now we'll be using the term intermolecular forces. Intermolecular forces are attractive forces that are between two molecules. Do not mistake these as intramolecular forces, not else you'll lose like 8 marks on a question, like me last year. Don't make that mistake, you guys are smarter than that. Now, we'll be going through some examples of different types of intermolecular forces. There are 3 types that we're going to be talking about today, and the first one is the London dispersion force, or also known as LDF. The other one is going to be the dipole, and then the last one is the hydrogen bonds. And these are the strongest. So let's take out a different color pen and let's rank them from 1 to 3, 1 being the strongest and 3 being the weakest. So this would be the weakest, London dispersion. Dipole is the second strongest, and then number 1 is the hydrogen bond. Something interesting about our human body is that hydrogen bonds are basically what we're made of, and that's why everything that we have, our skin and tissue, are so strong. Now that we have that out of the way, in order for us to figure out if there is a dipole-dipole bond, we have to go through a series of checks. First, we have to check if we have the intramolecular force of a polar covalent bond. If we have that, then we figure out if our molecule is actually symmetrical or not. If we have an asymmetrical molecule, that means that we have a dipole-dipole. In order for us to see the properties of IF3, we need to figure out what inter- and intramolecular forces that are acting on the molecule IF3. So how do we do that is first we figure out if it has polar covalent bonds or covalent bonds through the delta En. So let's do a little delta En calculation right here, and take out your calculators if you need to. We're going to do 4.0 minus 2.5, and we got these numbers through the electronegativity chart that we had from beforehand, and 4.0 will be associated to fluorine, and the 2.5 will be associated to our iodine, and that means that our electronegativity number is, wait for it, 1.5. That means that our bond is a polar covalent bond through the number line that we looked at from the previous part of our video. And now that we know that, we need to figure out if this molecule is symmetrical or not symmetrical. Why? Is because people always think that if you have the polar covalent bonds, that means our whole molecule is polar. But it actually isn't. That is not the case at all. We have to actually test and see if our molecule is polar or not. And how do we do that? We take out a different color of pen and we see that we need to draw some arrows towards the more electronegative atom. So we're going to do that right here. More electronegative and more electronegative, and that is because fluorine has the higher electronegativity number from our chart. And now that we know that, we see these arrows right here. And what we need to do is similar to what we do in physics. When we have two vectors in our free body diagram, they need to cancel each other out, which means that we have no motion. That's just like how our fluorine is going to be. If our fluorine has arrows pointed one towards it like this, but then we have no arrow this way, we have no arrow that way, that means that, well, we have a asymmetrical molecule. And if we know that, then this molecule is in fact polar. And if our molecule is polar, we know that we have dipole attractions. And if we know that, we can figure out some physical properties based off of that. One of the biggest physical properties that we have is that it is actually very soluble in polar solvents such as water. So if we put an IF3 into water, then it will dissolve. And another thing that we need to talk about is the melting and boiling points. Since this has a stronger intermolecular force in comparison to our weak London dispersion forces, well, that means we have a higher boiling and melting point in comparison to non-polar molecules. However, it will have a lower boiling point and melting point in comparison to water. And that is one of the biggest conclusions we can make with our knowledge of inter and intramolecular forces. Another thing that we could think about is that since it has a lower melting point and a lower boiling point than water, when we are at room temperature, our IF3 has most likely a gaseous form. And that is because we have lower melting and boiling points than water, so it will be in a different state. Since liquid is the regular state of water in room temperature, we can assume that our actual state of IF3 is probably gaseous since it has a lower boiling point.